Hi, this is Miss Litton, and this is my wonderful period 4 class. Say hi.
Hi.
And this is Honors Biology, and we're just going to record the way neurons work. Are we excited?
Yes.
Yay. Okay, so I mentioned this once before. So along the length of a neuron, when you're trying to get a message from point A to point B, along the length of the neuron, what kind of message do you have? Electrical. But where two neurons meet, or a neuron meets a muscle or a gland, what's the message going to be? Perfect. Okay, so here I have drawn a lovely neuron for you. What would be this region up here? Dendrites. Okay, and what's missing out of the middle of this? Well, this is the cell body, but what's missing out of it? The nucleus. So there's some things a little bit absent in my neuron. What's this long part right here? Axon. And these are the little feet are like axonal bulbs. Okay? So along the length of this, we're going to have an electrical message. At the end of it, we're going to have a chemical message. Now, do you remember back when we talked about how things cross the cell membrane? We said you could use a channel or a carrier. And if we go against the concentration gradient, what is that called? Active transport. And what do we call them when you use proteins in active transport? It starts with a P. A pump, okay? What is the most prolific pump of all? The sodium potassium pump. 30% of all the ATP you generate in your body is dedicated to your sodium potassium pumps in your body. So just imagine your dinner last night, okay, whatever you had. Imagine 30% of that dinner, it's going just to what we're going to talk about right now, sodium potassium pump. What the sodium potassium pump will do is it'll pump 3 sodiums to the outside of the neuron, the outer edge of the neuron, and 2 potassiums to the inside. Sodium potassium pumps never stop. They don't go, whew, done. Never, never, never. They keep going, and they're doing it on both sides of the membrane. So they're doing it over here. I'm just showing it to you on one side. Where's my little K? That's not it. That's it. All right. So if we keep pumping 3 sodiums to the outside and 2 potassiums to the inside, they both have what charge? Good. They both have positive charges. What can't go right through a phospholipid bilayer? Anything that is large or charged. So these 2 ions, if they're going to get across, they're going to have to use some sort of what? Channel. What do we call it when you go from a higher concentration to a lower concentration using a channel? It starts with an F. Facilitated diffusion. Okay? Does facilitated transport cost you any energy? No. If sodium goes from the outside to the inside using a protein channel, is that going to cost you anything? No. And that's the direction it's going to want to go. It's going to want to go from a higher concentration to a lower. Where's potassium going to want to go? Potassium starts with a K. Or that's it simple. It's going to want to go where? Yeah, potassium. All right, sorry. So potassium's going to want to go out. This setup like this, if no gates open and they can't move, this is a charged battery right here. We have more positive charges outside than we do positive charges inside. Why is that? Youngest bio buddy, explain that. Why more positives out than inside? Because, fill in the blanks, we pumped out what? 3 sodiums out and 2 potassiums in. So there's an unequal amount of positive charges between the outside and the inside. Which side is more positive? The outside. Okay? Now let's add to this differential. In addition, there are negatively charged ions and proteins inside the neuron, like chloride. Chlorine is a negatively charged ion. So not only do we have more positives outside than inside, but we have more negative ions on the inside, again, taking us more negative. Also, third and finally, the potassium right here, the K, the gates that keep them inside, some of them are leaky, and so sometimes potassium leaks outside, furthering the difference. So you might be at about -65 up to even -70 millivolts difference. Negative on the inside, positive on the outside. 3 things cause that. What 3 things? What was the first thing that caused this differential? The sodium potassium pump. Who pumped 3 sodiums out for every 2 in? Did that cost us energy? Yes, because you're going against the gradient. You keep piling up sodium outside and you keep piling up potassium inside. Yes? So that is going to cost you energy because you're going against the gradient. You're putting all the red balls over here and all the blue balls over here. Does that make sense? That costs energy. They're going to want to go the other way. That won't cost you energy once you open up their gates. Okay? Sodium potassium pump is the first thing. Second thing that caused a difference is what kind of things do you have inside? Things that are what charge? Negative. So that creates even more of a difference. And then third thing, we have leaky what kind of gates? Potassium gates. This is a neuron at rest. If you could say a neuron wasn't firing, it was just resting, that's the setup all the time. Okay? When you want an action potential to occur, let's say we have some neurotransmitter that lands on these dendrites. If it is excitatory, the way what it will do is it'll start to open up sodium gates. Well, you know the way sodium wants to move. Sodium wants to move where? In. So once you get this one to come in, it's more likely that you're going to get the next one to come in if you reach the threshold, and the next one, 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 all the way, and you go from point A to point B. And if that message, that reversal of charge, it's like if you lined up dominoes in a row, and you would think they would go, brrr, and all of a sudden the dominoes would fall over, right? Once you trigger one, you're more likely to trigger another. Once you get to the end, and we'll talk more about the synapse in just a minute, then that could release a neurotransmitter from the end of this neuron, okay, at this axonal bulb, and it could be stimulating the next neuron, the muscle, or the gland. Okay? So it is a quick reversal of charge. That is the action potential. This reversal of charge, because now when sodium comes in, now we have all the positives inside, so the inside is going to switch from being what? Negative to positive. That's how you get a message from point A to point B. Now I'm going to talk about the fix in just a minute, but I want who? Old, young? I don't know whose turn. Old. Old. Talk about an action potential. Actually, I take it back. Old, you describe a neuron at rest and the 3 things that put it at rest. Young, you describe the action potential. Go. You can do this at home too. All right, come back to me. So, we have reversed the charge along the length of the neuron. That is a nerve firing. That is a neuron firing. Go from point A to point B. Now, if I want this neuron to fire again, I got to fix it. The quickest fix of all, is to start having potassium gates open up. Because sodium Sodium came in, if the potassium gate opens up, then it will replace the positive charge that came in. Now I'm starting to even it out a little bit more. So then potassium comes in. Hi, sweetheart, how are you?
I'm good, how are you?
Good. Okay, and potassium comes out again and again and again. This will restore the amount of positives on either side of the membrane. So now we'll have more positives on the outside than we do on the in. But if this keeps happening, right, we'll have the ions on the wrong side. So the long-term fix, once again, is the sodium-potassium what? Pump. Pumping 3 sodiums out for every 2 what? Potassiums in. Okay? Let me give you an analogy, model this for you. Let's say it's a Friday afternoon, let's say a little bit later, 6:30. You want to go out with your friends. And your mom says, sure, you can go if your room is clean. Now let's just, I don't know the state of your room right now, but let's just make your room a mess in your mind. I know for some of you that makes you uncomfortable, okay? But let's just pretend your room is a mess. But you need to go now because they're going to arrive in like 10 minutes. So you're like, oh, I have to have a clean room. So what's the fastest way to clean your room? Shove things in your closet, shove things on your bed, and it looks clean, right? That's your quick fix. But if you kept doing that forever and ever, you wouldn't have any clothes in any spots you could find them. So your long-term fix is to fold your clothes and put them away in the right spots, okay? So the quick fix to reset a neuron so it can be used right away is to allow that potassium to go out and take sodium's place. The long-term fix is your sodium-potassium pump, restoring the sodium to the outside and the potassium to the inside. Now, as far as speed goes, as soon as the sodium rushes in, it's like this, brrr, and right behind it, brrr, the potassium is rushing out. So it's ready to go, and it's golden right then. But what's happening the whole time? What never stops? What never rests? The what? Sodium-potassium pump. So long-term fix is always going no matter what, but it's not going to be as fast to restore a neuron as letting the potassium go back out. Yes?
So the sodium, when it comes in,
yes,
and then it opens like a bunch of other gates along the thing, can the potassium only go out those gates too, or is it a
No, it cannot, because we know that proteins on membranes are very, very what? Specific. So if it's a sodium gate, it's dedicated to sodium. If it's a potassium gate, it's dedicated to potassium.
So when there's one potassium gate that opens, does it trigger a bunch more to open too?
Yes, it's the same thing. It triggers the next one and the next one. Okay. They are called voltage-gated channels, and so it's like a repelling force that pops them open. Yeah. Okay, so that is an action potential, and I hope that was helpful. And have a piece of toast. Make good choices.